Hey, here's a video on some math I've been doing just for fun. So let's just start with the natural numbers. So I'll just write them here, 10, 11. And maybe I'll just stop there. So that's the first 11 natural numbers. And below these, I'll just write the first 11 prime numbers. So the first prime number is 2, 29, 31. Here is the first 11 prime numbers. So what p is p is a function that goes from the natural numbers to the primes, which I'll just write in this blackboard p. Let's write p of n is the nth prime number. So for example, p of 1, we can just look up here. The first prime number is 2. Let's do another example. P of, 5. The fifth prime number is 11. Now I'm interested in another function which is p inverse. So this is a function that is from the primes to the natural numbers. P inverse of 2 is equal to 1. P inverse of 11 is equal to 5. In general, P inverse of P of n is just equal to n. So let's try that. P of 1 is equal to 2, and then P inverse of 2 is equal to 1. Now I was looking at the prime numbers a while ago, and I was thinking, this is kind of like renaming the numbers to have new names. You can look at this relationship between these two rows that way. So for example, 1 has the new name 2, 2 has the new name 3, 3 has the new name 5, and so on. And when you look at it this way, you can imagine, let's say we rename all the numbers. We still have a memory of what the numbers' previous names were. So, for example, we have a new number 3 and a new number 5, but we remember, hey, there was a number in between 3 and 5. There used to be. So I'll just write that number here. Hey, there used to be a number 4, right, in between 3 and 5. And then in between 5 and 7, hey, there used to be a 6. And in between 7 and 11, there used to be 8, 9, 10. And between 11 and 13, hey, there used to be 12. And there used to be a bunch between these as well, but I'll just do some dots for now. The thing you might notice as well is going this way is p of n. So p of 1 is 2, p of 2 is 3, p of 3 is 5. And going in this way is p inverse of n. So p inverse of 2 is 1, p inverse of 3 is 2, p inverse of 5 is 3, p inverse of 7 is 4, and so on. So now there's this interesting thing. What is p inverse of 4? Because there's no natural number right there. But is there something which I could put here and say p inverse of 4 is equal to this? P inverse is just only defined for the primes. So 4 it's not actually defined for, so it's not a valid input to p inverse. But could we come up with a p inverse that is from the natural numbers to, I don't know. What is p inverse of 4, for example? And there's not an obvious answer, but maybe we can make up some math and see what happens. So I came across a really interesting way to decompose numbers that relates to this and can actually help us figure out what p inverse of 4 is. We already know, or well, we probably already know, how to decompose numbers into primes. So for example, let's just start with 9. We can do a factor tree and see that this is 3 times 3. 15. This is 5 times 3. 24. This is 24 is 3 times 2 times 2 times 2. So we can break down numbers in that way, but there's actually a way to break down prime numbers even. And this will lead to an interesting way to visualize or to a new notation for numbers. Part of being able to decompose numbers into their primes is that there is actually another way to write numbers. For example, 9 can be written as 3 times 3, and for example, 15 can be written as 5 times 3. And this is a way to write numbers just in terms of the primes that make them up. I'll just go back to the numbers again. We already know 2 is equal to p of 1. It's the first prime, right? And we know that 3 is the second prime. So we can write it like this. But we actually know a different way to write 2, so we can write it like this. So this is the same as this. How about 4? So here's where we have to, this is equal to 2 times 2. And then we can decompose that into p of 1 times p of 1. We can decompose 5 into, what is 5? It's the third prime, so it's equal to p of 3. P of 3 we already know can be written as p of 2. Or sorry, 3 can be written as p of 2, so p of 3 is equal to p of 2. And we actually know how to write p of 2 as p of 1, so 5 is actually equal to p of 1. And we can keep going on and breaking these numbers down into nested prime functions, nth prime functions, and multiplications. So let's just do 6 because it's another good example. This is equal to 3 times 2. And we know how to write 3. That's equal to p of 1, just to skip a step, times p of 1, which is 2. So that's a way to write 6. And we can simplify this or come up with a new notation to represent, to write this down in an easier way. And that notation will just be just circles to represent p. So for example, let's just let 1 equal emptiness, and let's let 2 equal a circle around emptiness. So p of 1, this is a circle around 1. 1 is just nothing. 3 is p of 2, so it's a circle around 2. So it's a circle around 2. Or in other words, we already know we can write 2 as a circle, so we can write a circle around a circle. And 4 is 2 times 2, and the way we'll write times is just by putting circles next to each other. So we know 2 we can write as just a circle around nothing, so 4 is 2 circles next to each other. 5 is p of 3, so a circle around 3, and we know that 3 is 2 circles, so this is a circle around 2 other circles. And 6 is 3 times 2. We know 3 is 2 circles, 2 is 1 circle, so 6 can be written like this. And I'll just keep going on because I've already figured out what these are. Well, 7 is p of 4 actually, it's the fourth prime. And 4 is just 2 circles, so it's a circle around 2 circles. 8 is 2 times 2 times 2. 9 is 3 times 3. 10 is 5 times 2. Oh, sorry, it's getting a bit messy. And 11 is actually the fifth prime. So it's a circle around a circle, around a circle, around a circle. So we can write any number using some nested circles, like they're circles beside each other. So an interesting place we can go with this next is now that we have the circle notation, p of n, we can write it as just a circle around n. That's the notation we made up, right? And we can come up with this other notation here. P inverse of n is equal to a red circle around n. And then we have this rule here where if we have a circle around n and a red circle around that, we know that P inverse of P of n undoes P of n, so this is just equal to n. Now we can define what P inverse of 4 is, because we know 4 is just two circles from the previous page. So P inverse of 4, we can define this new notation and new number. We'll just write it like this. And P inverse of 6, for example, let's try that one. Well, we know what 6 is. It's 3 times 2. Here's 6. And here's 4. Here's 6. So here's how we write P inverse of 6. And you can actually do this for 8, 9, 10, well, for all numbers actually. And you can do something even more if you consider P of n. So what's the second prime? The second prime is 3. What's the third prime? Sorry, this is getting a bit cramped. The third prime is 5. And what's the fifth prime? The fifth prime is 11. What's the seventh prime? 17. 11th prime, that's 31. And I can't keep going right now because I didn't write those down. But if we do the same thing here, we can remember there used to be some numbers in between 3 and 5. Or there is some numbers in between 3 and 5, to put it another way. And between 5 and 11, there's 6, 7, 8, 9, 10. And we can do something pretty interesting here, whereas we can define what P inverse of 4 is. So P inverse of 4, we already know it's right between 2 and 3 here. And in this number line it is as well. And then we can find out that P inverse of 4 is actually between 1 and 2. So there's a way to come up with what P inverse from the natural numbers is, and it goes to these other numbers which are a combination of writing numbers as P and P inverse. So maybe we would call it the red circle numbers or something like that. So thanks for taking a look.